All right, we're starting chapter 10, 12 notes. So most of this chapter will be from chapter 10, but there is a little bit from chapter 12 towards the end of this that we'll cover. Because I'm not here, I cannot teach you the page 1 and page 2 of the notes. It's using a technique called the right-hand rule, and I kind of have to show you that rather than having a recording. So we are actually going to start on page 3 of the notes. So in math class, I'm pretty sure that you have talked about cross products before, but let's just kind of review. A dot product you've done before with, like when we did work. So when you have vectors that look like this, A with a dot in the middle and then vector B, that's defined as a dot product. And that's just the magnitude of A times the magnitude of B times the cosine of the smallest angle between them. And this gave you a scalar. So we did that back when we did work. We said that work is F dot X or F dot S. Well, this new thing that we're going to learn about, angular momentum, and then the old thing that you already know, torque, those are actually found using something called cross products. And cross products kind of look sort of like a dot product, except instead of a dot, there's a cross in between them. And by definition, this is a mathematical term, a cross product is the size of A times the size of B times the sine of the smallest angle between them. So you can see where dot is a cosine, sine, cross products are a sine, but what this does is it gives you a vector. And the direction of the vector, you can use a technique called the right-hand rule, which is described on pages 1 and 2, which I will teach you when I come back. So we're going to use the word right-hand rule in these notes, but then we're not going to worry about the directional aspect today. We'll add that to the notes later. So this first term that we're going to talk about is something called angular momentum. And angular, as you know it right now, pretty much means rotational, but you're going to find that there's something a little different about that with this. And then momentum, you've used the word momentum before in physics. So back when we learned about momentum before, we used the variable lowercase p with an arrow equals mass times the velocity. And that's what linear momentum was. So what we're going to do is we're going to learn about the equivalent of linear momentum, and we call it angular momentum. So in formulas before where we've had a P, we're now going to replace them with a capital L with a vector arrow over it. And so we're going to use this diagram, this three-dimensional grid, as something to help us describe what it is. So I want you to imagine this is like a room in a classroom or something like that. And I've got a particle. We'll just put the particle here in the XY plane. And let's say that that particle is a distance r away from the origin. And that particle happens to be moving with a velocity, again, in the XY plane that's given by that direction. And if its velocity is given by that direction, then its momentum would be given by that direction as well. Because momentum is just mass times velocity, and mass can't change the direction. So this would be the direction of its velocity and the direction of its momentum vector. Well, if you extend out the radius and extend out the momentum vector in this formula that you're going to see in a moment, this angle that it's referencing is the smallest angle between those two lines. So it could be this angle or this angle by vertical angles. So one way that we define angular momentum is, again, the variable is a capital L, and it's defined as r cross p. And I know this isn't a multiplication because you can't multiply vectors, so this is a cross product. And I just defined up above what the cross product is. So it just means it's the size of r times the size of the momentum, p, times the sine of the smallest angle between them. And what I've done here is I've just replaced p with mv back from when we did linear motion. So the formula is r is the distance away from some reference point. Again, from here it would be from the origin. M is the mass, that'd be in kilograms. V is the velocity, and then this is the sine of the smallest angle between them. Now this n hat, that is just your direction. And that direction is found using something called the right-hand rule, which I'm going to teach you about when I return. Angular momentum can kind of be thought of like linear momentum. Back when we did linear momentum, we called it the oomph factor. Like, you know, if something were going to be running towards me and run into me, the more massive it is and the faster it is, the bigger I'm going to say oomph. Well, angular momentum is kind of like that. So we can kind of think of it as the damage done due to rotation. So if you've ever accidentally put your hand or your finger in a fan blade, or in a, you had a bunk bed and you put your head in a ceiling fan, you know that those do some damage. The faster they're moving, the more it hurts. The more massive it is, the more it hurts. So this is kind of the damage associated with something that is rotating. You can sort of think of it that way. And so you can see below here is where we defined what this is. Theta is the smallest angle between R and P. N hat is the direction of this angular momentum, and the direction is actually found using something called the right-hand rule. And again, you'll learn about that later, but what you're going to learn is the direction of this cross product is actually a third dimensional vector. So if in this diagram the particle is in the XY plane, then the angular momentum would be in the Z plane. So it either would be positive Z or negative Z. And we'll fill this in later once you learn how to do the right-hand rule. The units of angular momentum, we can just kind of create them from the units here. So I'll create them off to the side. So R would be a meter, M would be a kilogram, and then velocity would be a meter per second. So then if I simplify that, that would just be a kilogram times a meter squared divided by a second. This is not a Newton. A Newton, the seconds is the squared, and the mass, or the meters isn't. This actually, though, is a joule times a second. I never use that unit. I always just do kilogram meter squared per second. What's kind of interesting about angular momentum, though, is a particle does not actually have to rotate or revolve in order to have angular momentum. And that's different from everything we've done so far with rotation. So this chapter is still a rotational chapter. So in order to have angular momentum, it just has to be a distance. Your particle has to be a distance away from some reference point. It has to have a mass. It has to have a velocity. And this angle cannot be 0 or 180 degrees. If it's got all of those things, a distance from a reference point, a mass, a velocity, and an angle that is not 0 or 180 degrees, then it's going to have angular momentum. So you're going to kind of have to get used to that idea. So then there's another formula that we can use for angular momentum as well. And this formula is for objects that are spinning or rotating on a symmetry axis. So things that do rotate can have angular momentum. So say, for instance, a merry-go-round or a record on a record player. But if it's rotating around a symmetry axis or an axis of symmetry, then I can also find the angular momentum just by creating it from the linear momentum formula. So back when we did linear momentum, we said linear momentum was mass times velocity. So if we create that, instead of P, we now have this capital L for angular momentum. And then instead of M, we use I. Again, this is from last chapter. And instead of V, we use omega. And omega is actually a vector too, using the right-hand rule, which I'll teach you later. This does have to be in radians. It's one of those little baby 3 formulas. And so the omega in here has to be in radians. So what we're going to do is we're going to practice this with a couple different examples. So if you go to page 4, example 2, it says a hollow sphere. So that's important. So hollow sphere. And you can't forget about those formulas. So the I value for a hollow sphere is 2/3 mr squared of radius 10 centimeters, or r equals 0.10 meters, and mass 10 kilograms. spins clockwise. Now, we'll deal with that clockwise thing later. As seen from above on a symmetry axis at a rate of 1 RPM, which means rotations per minute or revolutions per minute. So that's your omega. So 1 revolution per minute. And what I want is the sphere's angular momentum. So if I were to, accidentally stick my hand in there, how much would it hurt? I guess you could think of it that way. So for this one, based on what they gave me, I'm going to use the L equals I omega formula rather than the R cross P formula, because the R cross P would involve having to know the velocity and all that kind of stuff, which I don't know. This, though, is a formula where I have to be in radians. So let's quick change this 1 rev per minute to radians per second. So in 1 rev, there's 2 pi radians. And in 1 minute, there's 60 seconds. So if I do a little canceling here, I would just take 2 times pi divided by 60. This is going to be 0.1047 radians per second. And that's the value that I would have to have in this formula. So then I can start to put in what I need. For a hollow sphere, it's 2/3. The mass is 10. The R is 0.10, and that has to be squared because of 2/3 mr squared, times this angular speed in radians per second. And so then when I multiply all this stuff, I get 0.00698. And then the unit of it is a unit of I, kilogram meter squared, times a radian per second, but a radian is unitless, so it just takes the per second part. And then this does have a direction, but when I get back, we'll talk about it. So for right now, we'll just make a blank for that. So what I'm going to do is I'm going to stop this video. We have a couple more examples we're going to do, but I can only record 15 minutes at a time. So you're going to want to go and look at the second link to record to see how to do the next 2 examples.